All right, so let's go ahead and put it all together in a couple of examples. So we'll call this example 1. So we're going to use the leading coefficient test. We're just going to determine the end behavior of the function f of x is x cubed. That looks awful. Try that again. X cubed plus 3x squared minus x minus 3. So what we have to do is we have to look at two things. We have to look at the degree, and we have to look at the leading coefficient. And that's how we'll determine it. So the degree of this thing is the highest exponent. The degree of this thing right here is the highest exponent. It's not writing. There we go. It's 3. The leading coefficient is 1. It's not written there, but we have to assume that it's 1 because it's the number out in front of the highest coefficient. And that 1 is positive. So we have a degree of 3 and a leading coefficient of 1, which means the ends are going to go in the opposite direction. And because the leading coefficient is positive, it's going to start down and finish, up. Start down and then finish up. So that's how you're going to determine the end behavior of this thing. All right, a second example. Again, hopefully that one wasn't too challenging for you. What if it's not written in the same exact form? Obviously, there could be other forms that we're going to be given there. So maybe f of x is negative 4x cubed x minus 1 squared x plus 5. So this one is not in the same form as the one that's in the example 1. This one is in factored form, okay? So if you wanted to put it in the same way as it is in example 1, you would actually have to FOIL that whole thing right there. Then you'd have to distribute both of these things together by foiling it with that, and then it would be a real pain to do that. So we're not going to do that. What we're going to do is we're going to look at the idea of, again, just looking at the leading coefficients and the highest degree. Now here's the thing. If you did FOIL it, you would have to eventually multiply this term. Let's do that in a different color. You would actually have to multiply this term times this term and times this term. But don't forget that while you can't just distribute this square to here, that's not the way that works. Once you FOIL x minus 1 times x minus 1, you would eventually get an x squared as the highest power term from the inside of that parentheses. So you can't just distribute the 2 there to each thing. That doesn't work. But we're only trying to determine the highest powered exponent. So we're going to have something with an x cubed from the first one. We're going to have something with an x squared from the second one, and then we're going to have an x. If you were to multiply x cubed times x squared times x, well, that would have 6 total x's being multiplied together, so your degree here would actually be 6. So this is going to be an even, which means that these things are going to go in the same direction. And then you also have to look at the leading coefficients. Well, the leading coefficient here is 1. The leading coefficient here is 1, but the leading coefficient out here is negative 4. So multiplying 1 times negative 4, your leading coefficient, I'm going to start abbreviating that a little bit, the leading coefficient is going to be negative 4. And I know it looks like it might have just been negative 4 here, but you got to also take into account what's inside those parentheses, because those could also affect your leading coefficients. So our leading coefficient is negative, which means that both ends are going to go down. So it's a little bit more tricky when it's not in the standard form from example 1, but I don't think it's too awful if it's in the example 2. You just have to remember you've got to include every piece there. So if we were to take a look at Yeah, let's just do one more example real quick. This one should not be very difficult. So we'll say example 3, and then we'll move on to something else. So let's say we have f of x is negative 49 x cubed plus 806 x squared plus 3,776x plus 2,503. Main reason I want to do this specific example for the end behavior here is because I want to make sure that you guys are looking at the right things. The degree is still the highest exponent. That should not be difficult. That's 3. So that's odd. We know we're going to go in opposite directions for the end behavior. The leading coefficient, I'll just call it the LC for right now. I want to make sure you understand it's not the biggest number that's out here being multiplied times a variable, because in that case that would be this one right here. That's not the leading coefficient. The leading coefficient is always going to be the one that's multiplied times the highest power degree term. So our leading coefficient is negative 49, which means that my ends are, we already know they're going to go opposite, but because it's negative, that means it's going to end down. It's going to start up and end down, because the graph should generally go from top to bottom. All right, so that's probably that's probably enough examples of that before we move on. All right, finding the end behavior is obviously important, but it's not going to be enough for us to be able to sketch a graph really well. The next thing we're going to talk about is finding the zeros of a polynomial function. Finding the zeros of a polynomial function. Alright, in order to do that, and they call them the zeros because literally it's where the y value of the function, or f of x, equals 0. So it's when f of x equals 0, not to be confused with x equaling 0, it's where the function itself equals 0. For example, if I have f of x equals x cubed plus 3x squared minus x minus 3, what we want to do is we want to make sure that that function equals 0. So I'm going to replace f of x with 0, and then we need to solve that function. So a lot of this is going to involve factoring. A couple of points that I want to make over here. Zeros can be called several different things. Zeros can also be called the roots of a function. They can also be called the solutions of a function, and we've talked about this before. And they can also be called the x-intercepts of a function. So all 4 of these are synonymous, and you might hear or see all of them at some point. So just know that when you see any of those things, it means to do exactly the same thing. You're just finding or solving this equation for x. Make sure that it's equal to 0. So the polynomial must be equal to 0. Okay, in our particular example, let's go ahead and complete our example. In our particular example, in order to solve this one, we're going to have to factor it. And the only way we can factor this one, because it's got 4 terms in it and there's nothing in common, is to factor by grouping. So we're going to have the first group, x cubed plus 3x squared, plus, notice I put a plus there, even though you're like, well, wait a minute, there's a minus. That's true, but I can't chop the minus off, so the minus has to go with the x when I place it into a parentheses. So I'm going to group those first 2 things like that. Then what I'm going to do is I'm going to take out or factor out the common factor from each one of the parentheses. And the common factor in the first one is going to be x squared. That's the greatest common factor. Well, if I factor out x squared, that's going to leave us with x plus 3. Because remember, factoring is basically like dividing. I'm dividing it out. And then in the second one, there's nothing really in common there other than those minus signs. So I can factor out a negative 1, and that'll leave me with x plus 3. And really, that's what we want. What we are looking for is that this is the same as this. Because if the two parentheses are not identical, then this factoring by grouping isn't going to work. But in this case, the two parentheses are identical. And what you can see now is that this whole thing right here is one term. This whole thing is another term. The thing that's in common now is the x plus 3. That's the common factor. So now I can factor out the common factor of x plus 3 from each one of those. Well, if I take out the x plus 3 from the first one, that just leaves you with an x squared. And if I take out the x plus 3 from the second one, that just leaves that minus 1. So then it's factored down to this. And then what I have left over is x plus 3. And this x squared minus 1 is the difference of perfect squares. It does factor, it's a special one, to x plus 1, x minus 1. And then I'm going to take each one of those, set them each equal to 0, and then that's going to be my solutions. So you would have x plus 3 equals 0, x plus 1 equals 0, and x minus 1 equals 0. If I solve each one of those things for x, the first one I would subtract 3 on both sides, and we would get x equals negative 3. The second one I would subtract 1 on both sides and get x equals negative 1. And the last one I would add 1 on both sides, and I would get x equals positive 1. These are your solutions. Those are your x-intercepts. Those are your roots. Those are your zeros, any way you want to put it. That's what you would get there. So I could put that together with some of the end behavior that we should know. So let's go to red here. So the end behavior, now we can go back to the original to figure out the end behavior. Excuse me. First of all, the degree of this thing is 3. So it's odd. It's going to go in opposite directions. And the leading coefficient is 1, which is positive, so that means that it's going to generally go from down to up. Again, down to up. So let's see if we can just kind of quickly sketch this. If I were just to do a real quick sketch here, I know that I'm going to have zeros at negative 3. There's one right there. It means it's going to hit the x-axis at negative 3. It's also going to hit the x-axis at negative 1 and at positive 1. And I know from my my leading coefficient that it's going to go from down to up. So this is going to start down and it's going to finish up. Now we're going to talk about something else which is called multiplicities here in a few minutes, but it won't really affect this one. This one is going to go through this point, back down through this point at some place, and then back up through this point before finishing up. And that is a general sketch of the function x cubed plus 3x squared minus x minus 3. Alright, our next example is going to be a little bit different. We're going to take f of x equals negative x to the fourth plus 4x cubed, that is a cube, minus 4x squared. We're going to find the zeros. We're going to go ahead and find the end behavior, and then we're going to start to talk about this thing called multiplicity, which is going to play a role in this one specifically. So the first thing we're going to do is we're going to try and set this thing equal to 0 and factor it. So 0 equals negative x to the fourth plus 4x cubed minus 4x squared. So the first thing that I can see is, first of all, it's only 3 terms, but I do have x's in common here with every term. So I can actually factor x's out of this thing. As a matter of fact, because I have a negative in the front of here, I actually want to factor the negative out myself. I don't like having a negative out in front if I don't have to when I go to factor it in another way later. So I'm going to go ahead and factor out the negative, and I'm also going to factor out x squared. Now let's be careful here. If you factor out the negative x squared, that leaves you with a positive x squared there. If I factor out a negative x squared from the second term, that's going to make the second term negative 4, and then it's going to leave us with an x. And then in the last one, I'm going to factor the negative as well as the x squared, so that's just going to leave us with a plus 4. So when I go to factor what's inside the parentheses now, this should just factor like a regular trinomial. It's got to be an x and an x there. The factors of 4 on the end are either 2 and 2 or 1 and 4. 1 and 4 is not going to work because I can't take 1 and 4, add those two numbers, and get to the negative 4 in the middle. So it's going to have to be 2 and 2. And since it's got to be a positive 4 at the end, I either have to have negative 2 and negative 2 or positive 2 and positive 2. And because the middle one's negative, it's going to have to be negative and negative. So what I'm going to do is I'm going to set each, sorry about that. I'm going to set each one of these things equal to 0. So we'll have negative x squared equals 0, or we'll have x minus 2 equals 0, or we'll have x minus 2 equals 0. Well, if I solve one of them, I don't need to solve the other one. So I'm not going to write it twice. In the first one, I can divide both sides by a negative value and get that x squared equals 0. And then I can take the square root of both sides, which is going to give me x equals plus or minus square root of 0. But square root of 0 is 0, and there's no such thing as minus 0, so it's just 0. On the second one, I'm going to just add 2 to both sides, and I get x equals 2. So here's the thing that's interesting about this one. I've got two solutions. The highest powered exponent was a 4. So when we talk about this, we're going to go ahead and write our end behavior over here. The degree is 4. With a polynomial, the degree also tells you how many solutions or how many zeros you should have. Because this is a degree of 4, I should have had 4 solutions, and right now it looks like I only have 2. Technically, however, I actually have 4. I'll explain how that works in a second. And then we're also going to have to talk about the leading coefficient. So the leading coefficient here is -1, which means that this is generally going to go from, it's going to, well, not generally, because the degree is 4, the ends go in the same direction. So this is going to finish and start both down. So down and down. So now let's take a look at a sketch of this, and I'll explain what's going to happen here in a second. So the first thing is, we know we're going to have to put our zeros at, looks like 0 and 2, so I'm going to have to go out at least a couple in each direction here. So I'm going to have a 0 at 0 and 2. And according to this, my ends both must finish down. So it's going to have to go that way. It's going to have to go that way. The problem is this thing can't just go up and come back down through there. And that's because one of the other things that we haven't talked about is how many times a function, a polynomial, is going to turn. Since this is a degree 4, it's actually going to turn 3 times. It will always turn one less time than the degree. So in this case, just going up here and then coming back down actually doesn't work. That's not going to work at all. So I'm going to go ahead and erase that, because that's only turning once at the top there. So let's get rid of that, because that's not actually right. What this thing actually does, and again, we'll talk about how or why it does this. What this thing actually does is it comes up here and it bounces off of here, comes back down, and it comes up there and bounces back off of there. Now you can see it actually has 3 turns in it. It's still smooth. It's not discontinuous, so it's a polynomial. And because of this, it's actually going to have the right amount of solutions. Now, one thing we haven't talked about was this thing called multiplicity. And what happened here was that this and this both occurred twice. Now you can clearly see that that one occurs twice. I have x minus 2 twice. Technically, I should have written x minus 2 equals 0 and x minus 2 equals 0 and solved it twice. You don't have to typically do that, however. But this one here actually occurred twice. So we say that it has a multiplicity of 2. It occurred twice. And technically, this 0 also occurred twice because really, I have x squared equals 0 in the step right above, which technically could be written as x equals 0 or x equals 0, because technically x squared is x times x. So that also has a multiplicity of 2. When you have a multiplicity which is even, so a multiplicity of an even number, the graph will, for lack of a better word, bounce off the 0. As you can see here, the multiplicities bounced off the 0. It did not go through the x-axis. If you have a multiplicity which is odd, very much like we had in the previous example, the graph will go through the axis, or the 0. Alright, very important concept. So if the multiplicity is even, it's going to bounce off the graph, as you see in the one that we just did here. If the multiplicity is odd for your specific 0, the graph will go through the axis to the other side. It will actually cross all the way through. So that's one of the things that we have to decipher here with this. So we're going to talk about the multiplicities and put all this stuff together in one more example here.